So today I want to concentrate on, solving this equation. Okay? So although we have solved this equation in abstract, so to speak, we haven't really ever talked about its theta or phi dependence, right? Have we? So for example, we talked about LM, right? So this is a ket. But if I take a direction in my space, say it's given by a unit vector n. So n is given by essentially two angles, right? Theta and phi. Right? Because it's the x component is what? R is 1, and then we have sine theta, cosine phi, and the y component is sine theta, sine phi, and the z component is cosine of theta, right? This is n, the unit vector. So if I take this inner product, that is the direction basis, and then we look at we take the sandwich between L and M. That's basically what I'm calling L of M theta phi. Okay, is that clear?
Yes, sir.
Okay, so the solution to this equation are called spherical harmonics. Okay, so solutions to L squared y L M theta phi equal to L plus 1 h squared y of Lm theta and phi. These are known as spherical harmonics. Okay, and they are two problems with spherical symmetry. What the momentum eigenstates are to problems in which the Cartesian coordinate system is more appropriate. So if you remember, if I have some wave function psi of x, we can just express it in terms of a of p e to the power minus I, kx minus omega t, blah, blah, blah. And this was the Fourier expansion. And here, essentially this is written in Cartesian coordinate system. But if the system has spherical symmetry, then this is the basis that we want to use. Okay, so that's the linear algebra functional analysis point of view. Okay, so let's make some comments about the spherical harmonics. Now, since L, L satisfies the angular momentum algebra, right? Which means that the M quantum number is related to L in this way. If I give you L, then M can go from minus L up to plus L, right? So M takes how many values? 2L plus 1 values, right? So this is something we have proved before. But since L is orbital angular momentum, since it's not a spin angular momentum, but orbital, what are the allowed values of L? Can someone tell me?
Integers only.
Positive integers, yes.
So does it have to be positive?
Yeah, by definition, L is positive.
Oh, yes.
Okay. And and that's because L squared is a positive definite operator, right? So if you take, because it's a squared operator, right? It's Hermitian. So for any state,
Yes.
if you have L squared, if you sandwich it between psi, then you can write it as L acting on psi. This is some state, and that state can, and then here you have psi L, right? L dagger. So this is, a state, and so this is right. So, eigenvalues will be positive, definite. Okay. Okay. So, we will solve this problem without solving it. Okay. So, because L squared y Lm theta of phi equal to L plus 1 h squared YL of m theta and phi. What kind of differential equation is this? If I write it as a differential equation, is it first order or second order?
Second order.
Right. So, but you see that we know that Lz acting on YL of m theta phi is going to give me m h bar y theta phi, right? Lm. But what is Lz? Lz is minus I h bar d by d phi y of Lm theta of phi is equal to m h bar y L of m theta of phi. Now, if I assume that, it's, if I integrate this equation, then we can expect, and this is a bit rough, but we'll see that it's true, that the spherical harmonics, its dependence on phi, the angle phi, will be of the form e to the power I m phi, right? Because this equation, it's a first order equation to solve, and it's just exponential, right? So by using the angular momentum algebra, the eigenvalue equations, we can solve this, we can find solutions to this equation without actually explicitly solving this equation. Okay. So we are going to use a technique that you will also see being used at the end of your analysis of the simple harmonic oscillator, which you are working on right now. So one thing we can do is that we can say, okay, let's start with the maximal wait state. Okay. So the maximal wait state is the state where the value of m is highest. So if the given value of is L, then the value of m, highest value is L, right? So if I apply L plus on it, what should I get?
0.
Right. And now what I do is that I use the explicit expression for L. The explicit expression for L is I h bar e to the power I phi I del by del theta minus cot theta del by del phi y L L. And that's equals to 0, okay? Now, what we say is that, okay, we are going to take the ansatz that YLL theta phi has the form of some function of theta times e to the power I L phi times f of theta. So this, if I take this ansatz and I plug it into this equation, then I get an equation for f. And that equation for f is just f df by f of theta is equal to L cot of theta d theta, okay? So we can solve this, and the solution is simply f of theta is some constant e to the power c, let's call that c, times sine theta to the power L. Okay? So this is just if we integrate this equation, okay? So if I now combine the angular parts, then I get y LL theta of phi, some normalization constant, e to the power IL of phi, sine of theta of L. So this is our first solution. See, we have one of the states, and this is normalization. Okay.